Okay, so if you look at the potassium cycle that was just shared on the previous, oops, that's hard to see, isn't it? This is the potassium cycle that was shared on the previous slide. So what we're going to do is we're going to go in the potassium cycle, we're going to talk specifically about the mineral phases and then the non-exchangeable and then the exchangeable and probably the soil solution phase. And so the first thing I want to talk about is the primary mineral phases that are present in some of our soils and most of our soils, really. Depends on where you're located, I guess, in terms of the weathering scheme of soils across the US or the globe. But the primary minerals, if you have primary minerals that are present that contain potassium, 90 to 98% of the total potassium in the soil is most likely in these primary minerals. And that is unavailable to crops during any given growing season. So what are those minerals? They are comprised of micas, which are muscovite or biotite. I'm not expecting you to remember these or the chemical composition or formula of each one of these, but if you look at the chemical composition, these two phases, these micas have potassium present in them. Another primary mineral are potassium feldspars, all right? Potassium aluminosilicates. That's what these are. They contain potassium. So when weathering occurs, potassium is released from these primary minerals, but this is slow. It's really slow, all right? And so the ease of weathering follows this order, and I'm not expecting you to remember this as well, but biotite weathers quicker than muscovite, which weathers quicker than feldspars. Regardless, these three mineral phases contain potassium, and they do weather over time, and they release some potassium to the environment. You should know that soils with low potassium minerals in the parent material and highly weathered soils certainly may be potassium deficient, right? So like I think about the soils in Ohio that have shown potassium deficiencies, and it's not that we lack potassium, but say in early 2023, we lacked moisture to force diffusion reactions to allow potassium in the root to see potassium. That was the issue. But soils that may be highly weathered or have parent materials that don't contain those primary mineral phases that contain potassium can be potassium deficient. In Ohio, our soils are relatively variable with respect to plant available and total potassium. And I'm going to share with you some data in this unit that shows you this. So in terms of soils in Ohio, and I guess in general, soils in general, the weathering, more or less, and the amount of silt plus clay and soil organic matter present affect potassium availability. And that should make sense based on the figure that shows you the potassium cycle. That the availability of potassium is driven by certainly clay and CEC sites, and it's driven in part by the weathering of primary minerals and the locking up of potassium inside the inner layer of 2-to-1 type clays. When we talk about the needs of crops for potassium, we oftentimes talk about something called the critical level, or the amount of potassium that's needed to maintain sufficiency in a crop. And that level varies by crop species, and you're going to see that in this unit as well. And so the needs of different crops, and thus the needs based on soil variability, are present in fertilizer recommendations. So when you look at fertilizer recommendations for corn or soybean or wheat in the state of Ohio and other states, you're going to notice that the amount that's needed varies based on soil variability. So is the soil coarse textured or fine textured? And what's the crop that we're growing? And so we're going to talk more about that in this unit. So stay tuned.